welcome to another module in this massive open online course. So, we are looking at the parallel form 1 for IIR filter implementation, alright. Let us continue looking at this with the aid of an example, alright. So, we are looking at parallel form 1 . And let us consider the following example, a very simple example. We have h of z equals 1 minus half z inverse divided by 1 minus 7 by 8 z inverse plus 3 by 32 z minus 2 equals 1 minus half z raised to minus 1 divided by 1 minus 3 by 4 z inverse into 1 minus 1 by 8 z inverse, which is equal to 2 by 5 1 minus, remember you have to split it into the partial fraction expansion. So, this is basically the partial fraction expansion plus 3 by 5 divided by 1 minus 1 by 8 z inverse. Okay. So, this is the partial fraction. So, these are the factors in the partial fraction expansion, and you can see each of these is a first order factor in the partial fraction expansion, alright. And now we are going to illustrate the PF1, that is the parallel form 1 structure for this IIR filter, okay. And therefore, it is very simple. Now you can see it has two factors. So, you will have two branches. So, this will have two branches. The top branch will be corresponding to the first factor, that will be 2 by 5 by 1 minus 3 by 4 z inverse. So, that will have a gain that is 2 by 5, and then z inverse three by 4, okay, and this is the first factor, okay, and the other one is naturally going to be, this is the bottom branch, three by 5, and this is the delay z inverse, and this is the gain 1 over 8, okay. And therefore, now what we have is, we have to add the outputs of both the branches. So, we have an adder and the output will be y of n, okay. So, this is basically your parallel form 1, okay. So, this is the parallel form 1. Okay. So, this is a parallel form 1 structure for the IIR filter. So, this is 3 by 4, correct. And similarly, now you have the parallel form 2. Another structure is a parallel form 2, where given a transfer function, a rational function in Z, you use a partial fraction expansion in Z. In parallel form 1, you use a partial fraction expansion in Z inverse, in this you use a partial fraction expansion in Z. Okay. So, this is your parallel form 2. And in parallel form 2 you have Hz equals Pz over dz. This is the partial fraction expansion, and perform on this. So, you perform partial fraction expansion, P of expansion, P of expansion in Z for parallel form 2. And therefore, the Hz, the transfer function can be represented as Hz equals delta 0 plus you have the first order fraction factor delta 1 1 Z inverse by 1 minus alpha 1 1 Z inverse plus a typical second order factor of the form delta 1 2 Z inverse plus delta 2 2 Z minus 2 by 1 plus alpha 1 2 Z inverse plus alpha 2 2 Z minus Z raised to minus 2. And the parallel form 2 structure is given as follows. Again, the general structure. So, this can be given as follows. So, you have your Xn and you have the top branch, which is simply the gain, once again that is your factor delta naught. Then you have a middle branch, that is the delay Z inverse, and then you have your term minus alpha 1 1 this is minus alpha 1 1 and here you have the gain delta 1 1. Okay, because it is delta 1 1 in Z into Z inverse, that is the factor. Okay. So, this is this, and then you have another of the form there is another delay. This is a second order factor. So, you have two delays, and then you have this delta 1 2, then you have the term minus alpha 1 2 and another adder here, and the output, and therefore, here you have another minus alpha 2 2 and delta 1 2 and this is delta 2 2 and this is basically, then now you can see all these three outputs can be combined, can be added together to yield the final output. Okay. So, this is the second order factor, and if you combine them, if you add them, so this is the top gain is delta naught, then you have the first order factor z inverse minus alpha 1 and delta 1 gain, then you have the second order factor that will be z inverse and z inverse minus alpha 1 2 delta 1 2 minus alpha 2 2 delta 2 2, all right, and well, that is the net parallel form. So, this is your parallel form 2. And now, let us do a simple example to understand this better. Once again, let us consider the same transfer function hz that we have been considering, but now do partial fraction expansion in z, all right, and that gives us the resulting factors, all right, gives us the partial fraction, the parallel form 2 structure. Okay, so, let us go back to our example, the PF2 example. And you have your hz one minus half z inverse by 1 minus 7 by 8 z inverse plus 3 by 32 z minus 2 equals z square minus half z divided by z square minus 7 by 8 z plus 3 by 32. Remember, because we have to do partial fraction expansion in z. So, now I can simplify this as z square minus 7 by 8 z plus 3 by 32 plus 3 by 8 z minus 3 by 32 divided by z square minus 7 by 8 z plus 3 by 32, which is equal to 1 plus 3 by 8 z minus 3 by 32 divided by z minus 3 by 4 into z minus 1 by 8. Okay. And now, let us expand this into partial fractions. You can quickly do this. Let us say this is equal to 1 over z minus 3 by a over z minus 3 by 4 plus b over z minus 1 by 8. You can see that the coefficient of z a plus b equals 1. Further, coefficient of z or negative coefficient of the constant 1 by 8 plus 1 by 8 a plus 3 by 4 must be equal to. So, minus 1 by 8 a minus 3 by 4 b must be equal to minus 3 by 32, which implies 1 by 8 a plus 3 by 4 b must be equal to 3 by 32. And solving this yields a equals, well, 3 by 10, b equals 3 by 40, which implies that now hz equals 1 plus 3 by 10 by z minus 3 by 4 plus 3 by 40 divided by z minus 1 by divided by z minus 1 by 8. Okay. And now finally multiplying numerator and divided by denominator by z inverse yields 1 plus 3 by 10 z inverse divided by 1 minus 3 by 4 z inverse plus 3 by 40 divided by 1 minus 1 by 8 z inverse, okay, and 3 by 40 z inverse, okay. And this is the partial fraction expansion in terms of z, okay. And then we are converting it into z inverse, because remember we can implement only delays, all right. So now we can implement this PF2, the parallel filter 2, the parallel form 2 realization, and that is given as follows. It's very simple. So I have xn, the constant gain is 1. So this top branch is 1, this is, well, this is z inverse 3 by 4, and the gain related to this is 3 by 10, and the final branch z inverse, and there is a gain of 1 by 8, and there is a gain of 3 by 40. And this will be added, all these branches are added, and then you get the output y of n. So you have xn, the top branch is 1, then you have z inverse, the gain 3 by 4, 3 by 10, plus the bottom branch which is 1 by 8, and the gain is 3 by 40, and all these are added, and this is your parallel form. All right. So basically what we have done is we have seen several structures for IIR filter implementation, starting from the direct form 1, direct form 2, direct form 1 transpose, direct form 2 transpose, that is transpose of both the direct forms, and finally the cascade form, and also the parallel form 1 and the parallel form 2, all right. So these are the several forms for IIR filters, correct. So you have the several different forms as I had outlined before, and that is your direct form 1, the direct form 2, the transpose of each of these direct forms, and the cascade form, and the parallel forms 1 and 2, all right. And each of them results in a certain number of adders and delays, and you can check that from the examples as well as the structures that we have illustrated, all right. So we will stop here and we will continue in the subsequent modules. Thank you.